Hi there. All right, in this video, we're going to be taking a look at the magnetism worksheet. Okay, and this is kind of crucial. This is what you really have to know for the Regents exam. There isn't a lot of mathematics with magnetism, but you are going to have to be able to draw magnetic field lines. Now, I did find this worksheet online, and there's some things I love about it, and there's some things that I don't. So we'll discuss those as we go through. But we start off, we have to remember that magnetism is kind of like electricity in the fact that you have both a north and a south pole, and that opposites attract and likes repel. And so we have to have a convention as to how we're going to define magnetic field lines, because magnetism is a field force. And we will always talk about field lines as showing the direction that a north pole of a compass would point if it were in that spot. Okay, and so for this one, first, draw the magnetic field of each of the following samples. So for this, our magnetic field lines will always go from north to south outside of a magnet. So we can start in between here, and this is one of the ones that you would probably have to do on a Regents exam. They'll have you draw 4 magnetic field lines. And so you want to go from north to south outside of a magnet. And usually they'll have you draw 4. Now, we also know, and you're going to do this in lab, but these field lines also kind of bend up around as well. But they go from north to south, and that arrow shows the direction that they would go, as such, like this. Do the same thing down here, down here. Now, you could draw them on the outside as well, or out here. And here, they're going to go away from the north, so you could have it going out like this, away, and into the south over here, in. Okay, but generally, they won't have you go that far. Now, if we look at part B, now we have 3 of them together, but the same rules apply. They're going to go away from out of the north and towards the south. And so I'm going to start here, and this is going to get sucked in over like this, whereas this will get sucked in like that. These are going to kind of push, or these are going to get sucked in like this over here. Okay, they're going to go out of the north like that, out of the north and into the south, as such, away from the north, away from the north, and obviously there'll be a south down here as well. That's not drawn, but we would have it here as well. But here, they would look like this. Okay, it's important to draw the lines, and it's important to have them make sure you're going into the south and out of the north outside of a magnet. Okay, we'll do this as well. If we put compasses here, if you were to draw a compass, this north pole would push it, so the arrow points away from the north and towards the south, because again, magnetic field lines show the direction that a compass, if you put a compass there, the direction the north pole would push. And so this one's going to go away. This one's going to go towards, and this one will go from north to the south. Okay. If we draw here, draw position of the needle. Okay, so south, it's going to be coming like this, towards the south. Here, it'll be going directly across from north to south. Okay. Which of the illustrations below is an accurate representation of the magnetic field? Okay. Again, we would have to know that this side right here would have to be a south. This would have to be a north. Okay. Here, they don't loop around, because if you look at what's wrong with B, here, if you put this as a north, okay, well, it's leaving the north, but here it's coming into the north, so it can't be that. If we made this the south, then it's coming into the south, but it's going out of the south, so it can't be that. And this wouldn't work as well. So B is not an accurate representation, because magnetic field lines are closed loops. Now, the thing I have not put in here, and actually I'm going to go back and just talk about this really quick, get rid of the south and north here. Magnetic field lines are actually closed loops. So this one actually goes through, and on the inside of the magnet, it's going to come through like that and then come out over here. And here like this, and here like this. And I'm not going to be able to draw them all in because I don't have that small of a pen. Okay? But these magnetic field lines inside the magnet are going to go from south to north, and they're going to be closed loops around and around. Okay, and we'll talk about that when we discuss the magnetic field generated by a current-carrying wire, something along those lines. Okay. Here, we've talked about Maria, and this is one that you've actually probably done, hopefully in lab already. Okay, but obviously, if you sprinkle iron filings, it's going to look like choice B. Okay, and we don't have to have the arrowheads here because we're just looking at the magnetic field filings, so there's no direction from the magnetic filings, only with a compass. If we look at 6, a magnet is surrounded by a magnetic field, which lines of force, which one of the following diagrams correctly represents. Okay, and for this one, it's got to be choice A. Oops, no, yes, choice A, because it's got to go out of the north, and so I was looking at these arrows, I got them backwards in my head. Okay, they're going to go out of the north and towards the south. Okay, now, I really don't. This is one of the things I don't like about this, and we're going to discuss this in the next couple as well, is that here they have these magnetic field lines all touching. Okay, so right there and right there, I don't like that. And the reason for that is that these magnetic field lines should never, ever cross. Okay, because if they cross, that implies that there must be more than one magnetic field at that spot, a larger magnetic field. And that's not the case. Okay. You can make a case for part C because it is going from north to south, but the reason I don't like it is because of this part up here. Because this part up here should look like this. These should be going around like that and up over like this, out of the north and towards the south. So I don't like the top part in C. Otherwise, that one, the interior doesn't look half bad. Okay. Number 7, which the diagram shows the direction of the compass. Okay, remember, it'll point away from the north and towards the south. So we know A is out, we know B is out. If we look, oh, I love C. C looks good because it's going away from the north. And here, not D, because again, it's going towards the north in that case. Okay. Number 8, which the following diagrams correctly illustrates it. Again, same deal. It can't be A because it's going out of the north and towards the south. Okay. It can't be C because the compass is pointing away from the south. It should be pointing to the north. But I really don't like B. Okay. And the reason why I don't like B is, again, because of this right here. These magnetic field lines should not be touching. And if you got on a Regents exam and you had them touch like that, that would technically be wrong. So while the answer is B, and the answer is D. Both of those are both really good answers. The reason why I don't like them personally is because they have them, again, this spot right here where they're all touching, and they should not be. Okay, so according to the worksheet, it's B and D. But again, we've discussed why I don't like them. Same with number 9. Okay, with number 9, actually, none of these are right. Okay, there should be magnetic field lines that go from north to south. So the answer they're looking for here is actually B. But the reason why this is a really big no-no is because of this right here. These should not be crossing. Okay, they cannot cross. Okay, same thing over here. They cannot cross. The worksheet answer says that they really like B because it is going from north to south outside of a magnet, which is what should happen. And if you have two magnets close by, we saw this in lab, there will be magnetic field lines that go from across like they have right here. That part is correct. But the fact that they have those magnetic field lines crossing each other is a big, big no-no. Okay? So you either you got to get rid of the crossing part here in order to make this work. Now, obviously, C is out, okay, because it's going from south to north. That's an obvious no-no, okay? Here, this doesn't look half bad. It is going out of the north and towards the south. So, I mean, A was probably the most correct on all of these, okay? D is out again because it's going from south to north. But they want B, and B is technically what it would look like. But you can't have those things crossing. Okay, and number 10, this is a magnet creates what's known as a magnetic field. Compass can be shown to show the magnetic field. Which following statements is true? If a bar magnet is broken in two, each piece will only have one magnetic pole. We know that that is false. If you take it apart, you'll have one north and one south. If you break a magnet in half, you'll have two basic magnets. We do know that like poles repel each other. That part is true. And the needle of a compass is a small magnet. That is also true. So the answer here we want is C. Choices 2 and 3 are correct. Okay, now we get into the current carrying wire. So show the current direction for the straight wire. Okay, so the current direction for the straight wire, remember we're talking about conventional current, so it's going to go from positive to negative. So that's going to go up like this. So that is our conventional current. I'll write that down, conventional. And I know we still don't like it. In fact, we know actually electrons move. But, okay, we go there. So if we look at this, remember the magnetic field that is created, and I'll put this in kind of a light blue, are circles that are going to go around that wire. And you saw this in lab with the compasses. The compasses showed the direction. And so if we do the compasses, those magnetic field lines are going to look like this. Yep. If we look here, put in the compass direction for the straight wire, so our current is going to be traveling from positive to negative. And so my compass direction because it's out in front, is going to be down like this. This is our right-hand rule. And I know this is tough for you to see, and I'm going to try and show it on this. Okay, and actually I'll flip it around because I'm reversed. But as I'm looking at it, my thumb is going to point towards the negative, so away from the positive towards the negative. That's the direction my current's going. And then my fingers curl. And so if this is my wire, my thumb is headed in the direction. This is my wire. My compass in front, my fingers are pointing down. And therefore, the magnetic field is going to be pointing down the page at that point. Okay? If we look at number 13, we're going to use the exact same thing. If we look at A, okay, and I'm trying to do this where you guys can see it. I'm reversed, but it's backwards. So it's going to go from positive to negative. So my current is headed in this direction. So I got to flip this around. And so the current's headed in that direction. So then my fingers curl like this. And so A is an accurate representation. If we look at B, now my current's traveling up the page. Okay, and now my fingers have to point like this, and my fingers curl. So here, my magnetic field should be going in the opposite direction as it's shown. So that my fingers should be curling in a counterclockwise direction, not a clockwise, so B is out. And we'll practice with this a little bit more too. Okay, following diagram shows 4 compasses. Okay, so again, we're looking at our current. So current goes from positive to negative. So there's my current. Current's traveling this way. And so anything that is parallel with the current is out. So compass 4 and compass 1 have to be out of there. And so since my current is traveling in that direction, it's going to be going compass 2. And I'll try and show that to you. So again, as my compass, my current goes in this direction. My fingers curl. So when it's out in front, like that, my fingers are, since it's brown behind, hang on. I'm trying to reverse it for the video, and it's going backwards now. It says it goes like this. My fingers are actually, I have it on the right? Yeah, okay. So then my fingers curl around, so it's going to go north to south. So it's got to be compass 2. No. Oh, I was wrong. I was incorrect on that. Actually, are any of them right? Yeah, it's got to be compass 2. Because that's my finger's going to point in the direction the North Pole will point. So it's got to be compass 2. Yes. This is tricky. It's one of the funniest things I have, and when I teach this and watching you guys try and do this is your hands kind of convolute around and stuff like that. It can be tricky, but just remember, we'll go through the right hand rules. So you watch them down there. You can write these on your reference tables as well. But in a current carrying wire, thumb points in the direction of the current, and your fingers curl in the direction of the magnetic field. The magnetic field shows the direction that a North Pole will point. Okay. So in that one, it was compass 2. I think so. Is that okay, compass 2? Yes, compass 2 is the correct answer. All right, number 15, given a point M in the magnetic field, trying a shoe-shaped magnet, which was correct, shows a magnetic force would act on a point charge at point M. Okay, so if you have a point charge, okay, or if you talk, not a point, pause there. Okay, I'm back. I really don't like this question because it shouldn't be a point charge. We should change this to a North Pole or a compass. Because if it's just a single point charge, just sitting there, the magnetic field is not going to have a force on it whatsoever. In order to have a force on it, that point charge has to be moving in a certain direction. And because they don't give us that, there is no force on it whatsoever. So if we kept this just as a point charge, the answer is none. Because if the point charge is just sitting there, then it's not going to have any force on it whatsoever. If instead they were asking what would happen to what would the North Pole of a compass point, that's going to be choice 2 because it's got to be towards the south. Okay. All right, and number 16, the science department has decided to build an electromagnet uses recalibrated compasses, which define as a compass needle pointing in the correct direction. Okay, so again, this is our right-hand rule. Okay, and so here we have our current going down. Here we have our current going down. Here we have our current going up. Here we have our current going up. Okay, and so anything that points parallel to the current or towards the wire or anything like that is out. So automatically B and D are automatically gone. Okay, so in this one, in choice A, we have our thumb pointing down because that's the direction of our current, and our fingers have to curl so that when they get to the front of the wire, they're going to be pointing in the opposite direction. So it can't be choice A. If we look at part C, now my thumb has to point up, my fingers curl, and so when it gets to the front of the wire, it's got to be pointing to the right. And so my answer is choice C. Okay. And that's where we're going to stop for this one. Again, this can be kind of confusing. Come see me, and I will give you some sample problems as well. Take a look at some of the should do's. Okay. The good news is the vast majority of this stuff has gone on the Regents. As far as how to find out the direction of a magnetic field created around a current created by a current carrying wire. So you don't have to know the right-hand rules anymore. Instead, you really have to focus on these things up here where they talk about the magnetic fields and which direction the compasses will point. So if that part's good, just know that it's always showing the direction that a north pole of a compass will point, then you're good. So hope that helps. Everybody have a great night. We'll see you later. Bye.